Welcome to the Deep Dive, the place where we turn complex source material into, well, knowledge you can actually use.
And today, our mission is to move beyond the superficial.
Exactly. I mean, if you've ever seen two things that trend together, like, say, ice cream sales and shark attacks, and you've wondered if one really causes the other.
Then you've hit the wall of simple correlation. That's why we're doing a deep dive into multiple regression analysis. It's the tool that lets you find the true signal in all that noise.
I love that, finding the true signal, because that's the classic mistake, right? Assuming that because two things happen together, one must be driving the other.
It is the fundamental error. Our source material really hammers this point. It's what we in data science often call omitted variable bias.
Omitted variable bias.
Yeah, it sounds technical, but the idea is simple. You see a relationship between, say, X and Y. But what you don't see is this third thing, W, that's actually causing both of them to move. It's a confounder.
You gave us that great classic example, the rooster.
Right. The rooster crows and then the sun rises. They are perfectly correlated.
Every single time.
And if that's all you measured, your conclusion would be obvious, but wrong. You'd think the rooster made the sun rise. The omitted variable, of course, is the Earth's rotation.
And you have to control for that to see the real effect of the rooster.
Which is 0. And this isn't just a farm story. Think about a real-world problem, the effect of education on income.
Okay, yeah. More education, more income. We see that correlation all the time.
We do. But there's a potential confounder, right? Something like, say, intelligence or IQ. It probably affects how much education you get and your earning potential later on.
So you can't tell if the money comes from the degree itself or just from the underlying intelligence that helped you get the degree.
Precisely. The effect is all mixed up. So the only way to get a real answer is to statistically control for that intelligence variable. And that's exactly what multiple regression lets us do. It mathematically holds one thing constant so we can see the true impact of another.
Okay, let's unpack that. This idea of control. How does a model actually, pull that off mathematically?
Well, it's actually pretty elegant. Instead of just one X variable predicting Y, the multiple regression model relates Y to a whole set of variables, X1, X2, and so on.
Each with its own coefficient, its own weight.
Exactly. And the power is in those coefficients, the betas. This is the absolute core idea. We call them marginal effects.
Marginal effect.
The coefficient for, say, X1 doesn't just show its simple relationship with Y. It shows the change in Y for a 1-unit increase in X1.
Wait, here's the important part, right?
This is everything. When all the other independent variables in the model are held perfectly constant.
That's the magic. Held constant. Let's make this real with that Butler Trucking Company example from our research.
Perfect. So Butler Trucking wanted to predict their total daily travel time. That's their Y.
And they figured it depended on two main things.
Two things. Miles traveled, which we'll call X1, and the number of deliveries made, X2.
And the model they built gave them a coefficient for miles traveled of 0.0611.
Right. So the interpretation is key here.
Yeah.
For every extra mile a truck travels, the total time goes up by 0.0611 hours.
But, and this is the key, that number is only true because we've already accounted for the number of deliveries.
It's been purified. The model has statistically filtered out the time delay caused by making more stops. If we'd ignored deliveries, we would have thought miles were more important than they really are.
So you get this clean, controlled estimate, but now you have to ask, is the model any good? How do we validate this?
We start with model fit. The traditional measure is called R-squared.
Right, the multiple coefficient of determination.
And for Butler Trucking, it was over 90%. It sounds amazing.
I mean, 90%, you'd want to frame that number. But our source material had a huge warning about R-squared. It's kind of a vanity metric.
It absolutely is. And this is a trap for so many people. The flaw is that R-squared will always go up when you add a new variable.
Even if the variable is total nonsense.
Even if it's the color of the truck, it will never go down. And this pushes people to build these huge, overly complicated models.
Model bloat.
Exactly. Which is why we need a hero. And that hero is the adjusted R-squared.
Okay, so how is it different?
It's smarter. It takes the number of variables in your model into account. It basically penalizes you for adding complexity that doesn't actually help explain things better.
So if you add a useless variable,
your adjusted R-squared will actually go down. It forces you to be disciplined. It guides you to the simplest, most powerful model.
Okay, so that's overall fit. But what about the variables themselves? Are they all pulling their weight?
Good question. This is a two-step process. First, we run an F-test.
The F-test.
Think of it as checking if the engine is running at all. It asks, does this entire set of variables taken together have any real relationship with Y.
And if the F-test is significant, like it was for Butler trucking,
Then you know the engine is on. You've got at least one useful predictor in there somewhere. Only then do you move to step 2.
which is checking the individual parts.
Exactly, the individual t-tests. These tell you if each specific variable is significant in the presence of all the others. And for Butler trucking, both miles and deliveries passed their t-tests. They were both contributing something unique.
This is where things can get really messy, though, where the data can kind of fight back against you.
Oh, yes. You're talking about multicollinearity.
That's the one. It sounds intimidating.
It does, but the concept is pretty straightforward. It's just when your independent variables, your predictors, are highly correlated with each other.
So they're basically telling you the same story.
That's a perfect way to put it. A rule of thumb is to start getting worried if the correlation between any two of your predictors is, say, higher than 0.7.
So why is that a problem? If they're both related to the outcome, what's the big deal?
The big deal is that the model can't figure out who gets the credit. It becomes impossible to untangle their separate marginal effects.
So your interpretation gets all messed up.
Totally. The coefficient estimates become really unstable. They can swing wildly if you add or remove a little bit of data. And crucially, their standard errors get huge. They get inflated.
Which means?
It means you might see a variable that, logically should be important, suddenly fail its t-test and look like it's not significant at all.
You might even see a coefficient flip from positive to negative.
You can. The whole thing just becomes unreliable. If all you care about is pure prediction, it's less of a disaster. But if you want to understand the drivers, which is the whole point, multicollinearity is a 5-alarm fire.
Okay, let's pivot to something that really opens up what these models can do. So far, we've only talked about numbers. What about qualitative things?
Like region or gender or type of product.
Yeah. How do you put mechanical versus electrical into a math equation?
You use a clever trick called dummy variables, or sometimes indicator variables.
And how do they work?
It's simple. You just code a category as a 0 or a 1. For example, for repair type, we can say mechanical is 0 and electrical is 1. The category you code as 0 is called the reference category.
And there's a rule for this, right? The K-1 rule.
Yep. If your categorical variable has K levels or categories, you need K-1 dummy variables to represent it.
So for mechanical versus electrical, that's 2 levels. K equals 2.
So K-1 is 1. You only need one dummy variable. That's the example from Johnson Filtration, Inc. in our sources. They wanted to predict repair time.
Right, based on months since the last service and the type of repair.
So if we set mechanical to 0 and electrical to 1, the coefficient on that dummy variable, beta 2, tells you something very specific.
What's that?
It tells you the average difference in repair time between an electrical repair and a mechanical repair, holding the months since service constant.
So it's like a fixed penalty or bonus. If the coefficient is, say, positive 1.5, it means electrical jobs take an hour and a half longer, all else being equal.
That is a perfect way to think about it. It creates 2 parallel regression lines, one for each category, with different starting points.
So what if you have 3 categories, like sales regions A, B, and C?
Then K is 3, so you need K-1 or 2 dummy variables. You'd make one region, say region A, the reference. It gets a 0 on both dummies. Then one dummy captures the difference between B and A, and the other captures the difference between C and A.
Everything is measured relative to that reference point. Very cool.
It's incredibly powerful.
Okay, so that brings us to the end of this deep dive. Let's do a quick recap for everyone listening.
All right. Takeaway number 1. Multiple regression is your key to getting past superficial correlation. It lets you control for confounders to find the true relationship.
Second, and this is huge, ditch the raw R-squared when you're choosing a model. Use adjusted R-squared. It rewards power, not just complexity.
And third, don't be afraid of non-numeric data. The K-1 rule for dummy variables lets you bring all that rich categorical information into your analysis.
Now, for that final thought, something for you to mull over. We've talked about all the steps to building a good model, but this entire process rests on a foundation of statistical assumptions.
It does. Assumptions about the error term in the model. And thinking about those helps us understand a really critical distinction, the difference between precision and accuracy.
Okay, precision versus accuracy.
Precision is about consistency. Are your predictions all tightly clustered together? Accuracy is about truth. Are those predictions centered on the real value?
So if we follow all these steps F-tests, adjusted R-squared, we can build a model that is very, very precise. Our answers will be consistent.
Extremely consistent. But, and this is the scary part, If our underlying assumptions about the data are wrong, we can end up with high precision and very low accuracy, meaning our model is consistently and reliably wrong. We've built this beautiful, precise machine that is aimed at the completely wrong target.
That is a provocative thought. We all chase precision because it feels like certainty. So the question to leave you with is this. What big data-driven decisions being made right now in business, in policy, might be suffering from that exact problem? High precision, but fundamentally low accuracy. It's something this tool helps us spot, but only if we're willing to question our own assumptions.